Welcome everyone to our ACigs webinar series, webinar number 50. It's quite a big number. Today we have Chris Lawson with geosynthetic reinforced fields used in marine engineering applications. Welcome, Chris. We have also Brandon Swift, who will be doing Q&A, and Glenn Gillan, who is representing Solmax, our sponsor for the webinar. So we are ACigs is Australian chapter of IGS, International Geosynthetic Society, which gathers membership from most of the world, with lots of people joining from Geosynthetic Society. We do lots of events in Australia and New Zealand. So next one will be Best Practice Electronic Leak Detection webinar, which will be 27th of May. Presenters are still to be advised because we are talking to Australian leading companies with electronic leak detection testing. So you will see probably in a week in our bulletin who will be presenting that. In November, we have academic masterclass on geosynthetics, known also as educators. It will take part in Gold Coast, 24th to 26th November. We do invite all the academics to join us there. Next one, we are very excited about GINZ conference in 2027. It will be focused on mining, safer, greener, and smarter with geosynthetics, future-ready mining. It will take. It will be 6th to 8th of July 2027 in Pan Pacific in Perth. We thank you all the company members for supporting us. Without you, we wouldn't do any of these events. If you would like to join us as a corporate member or individual or student, please go to our website and join. Back to Chris. Chris is an engineering consultant based in Malaysia. He received his engineering degrees here in Australia and New South Wales, and he worked in the field of geosynthetics for the last 45 years. So you can get lots of knowledge from him about the marine engineering. I will not read all of it, but he's very knowledgeable. Thank you, Solmax, for sponsoring webinar. And so we'll have first the webinar, then we'll have a little presentation from Solmax, and at the end we will have Q&A session. So please post any questions, and we will read them and try to answer. If you need any certificate of attendance, please let us know. Thank you. And off to you, Chris.
Thank you, Alicia. Can you hear me okay?
Yes.
Okay. Thanks, Alicia, for introducing me. The title of my webinar today is Geosynthetic Reinforced Fields Used in Marine Engineering Applications. And what the contents of the presentation will cover, we'll start off with a pretty basic introduction on reinforced field structures. We'll look at the key differences between terrestrial construction, and by terrestrial construction, I mean construction on land, and marine construction. We'll then look at the two main reinforced field marine construction techniques, and that's basal reinforced seawalls and reinforced capping layers. We'll look at the key differences in reinforcement installation between terrestrial and marine construction. We'll have a brief look at the modes of failure of basal reinforced seawalls, and also the modes of failure of basal reinforced capping layers. And then at the end, I have 3 case studies, one from Australia, one from Vietnam, and one from Hong Kong. Now, just as an introduction, about the historical evolution of geosynthetics in marine engineering works. What we find is that geosynthetics have been used for many years for marine revetments, where geotextile filters have been used for over 50 years now. And you can see two photographs on the right where geotextile filters have been used in marine engineering applications. One behind rock armouring, and the second one at the bottom behind marine seawalls. So these have been used for many years now, and there's a big, long history of this. However, when it comes to the use of geosynthetic reinforcements, these really began as terrestrial applications, in other words, on land. And what's happened is a wide range of applications were developed on land since the early 1980s. So what we find is that today, the terrestrial applications of geosynthetic reinforcements are wide-ranging. However, over the last 20, 25 years, what we've witnessed is the use of geosynthetic reinforcements as they've expanded into marine structures where they offer specific benefits. And just to go back a little bit, some examples of terrestrial reinforced fill structures, which I'm sure you probably all find quite familiar. Over 50 years of use for reinforced soil retaining walls, reinforced fill slopes, basal reinforced embankments on soft foundations and over piles, and then reinforced capping layers over very soft deposits, all terrestrial applications. Now, when it comes to comparing terrestrial and marine reinforced fill structures, there's some considerations that need to be taken into account. And I've shown a table there, which on the left is listed the terrestrial structures, and on the right, the comparable marine structures. And first of all, let's start at the top. For terrestrial structures, the alignments and tolerances, you can control these pretty well. When it comes to marine structures, however, they can be difficult to control. When it comes to surface erosion for terrestrial structures, well, surface erosion is really non-existent because there's no water, whereas in marine structures, water erosion can be significant. There's no external water forces present in terrestrial structures, and the presence of external water forces can make installation difficult in marine structures. For terrestrial structures, we have the reinforcement placement above water, where specific gravity of the reinforcement is not important. But with marine structures, the reinforcement placement can be below water, where specific gravity becomes important. For reinforced fill structures, we're dealing with bulk densities for terrestrial structures, and for marine structures, we're mainly dealing with buoyant density of the reinforced fill, especially if it's below the water surface level. For foundation conditions, we can be dealing with slightly over-consolidated soft foundation deposits, whereas marine structures, we're normally dealing with normally consolidated or maybe under-consolidated foundation deposits. So it's very, very soft deposits. For reinforcement installation is relatively simple for terrestrial structures, and for reinforcement installation can be relatively complex, requiring large panels for efficiency. And we'll see that in more detail as we go through the presentation. When it comes to marine reinforced fill applications, today that really breaks into two different types of applications. First of all, the basal reinforced seawalls, as shown there in the middle diagram, where you have the soft foundation deposit, then you have the basal geosynthetic reinforcement on top, and then the granular fill used for the seawall, reinforced seawall. And you can see the photograph, typical photograph down below, where the basal reinforcement has been spread across the base of the seawall. And in this particular case, they're using dredged sand for the core of the seawall. It doesn't always have to be dredged sand. It can be granular materials used for the seawall, with the basal reinforcement providing stability. And the second type of application is for basal reinforced marine capping layers, as shown on the right, where the reinforcement is placed on the soft sediments. And these soft sediments may be contaminated, so you don't want these soft sediments to be disturbed and contaminating the surrounding environment. And then on top of that, capping fill is placed on top of the reinforcement to construct a capping layer, stable capping layer. And you can see a photograph of this in the picture below, where the reinforcement layer is pulled across the surface of the soft sediments, and then on top of that, a capping layer will be placed to contain and constrain the soft sediments underneath. Now, the key difference in geosynthetic installation between terrestrial and marine construction is really one of scale. And in terrestrial construction, normal typical scale is a typical roll size as it's produced in the manufacturing facility. And this may be of the order of 5 meters in width, this roll. And the roll is rolled out on site, and it can be manhandled or using special, pretty simple lifting equipment. And there it's put in place and then laid in place before the fill is placed on top. It's common to use overlapping on site, although sewn seams may also be used. So it's a fairly simple above ground installation process. When it comes to marine construction, however, normally dealing with large fabricated panels, as shown there in the right top photograph there, and you can see the strong guy underneath there. These can be very large panels, depending on how easy it is to use them and transport them to site and load them onto the equipment on site. And it can be a fairly complex type of operation, especially if you're installing the geosynthetic reinforcement underwater. For example, here in this bottom photograph, we have this very large, long, flat barge, where in these cases, the rolls of geosynthetic reinforcement are sewn together and fabricated on top of the barge. The barge is moved horizontally, and then the panels are then lowered and go up into the water, into the foundation and into the water to construct it. And this may be complex, and it's very large scale. Now, the key part about provision of fabricated panels for marine installation is you can either fabricate these in a factory or you can fabricate them on site. If you've got the area in the factory, it's always not easier to fabricate these panels in the factory, as you can see in the top left photograph here. And what you need is a large, clean, flat area to fabricate these panels. And to join these panels, they are seamed together, and they normally seam together with very good seam strengths for these panels, so they can take tensile stresses on the panels. And seam integrity is important for good panel installation. The size of the panels that you use, these can be limited depending on the transport availability to site and the distance that this has to travel. So here's some examples here. You can see here the panels laid out on site, and they're fabricated together, sewn together. Here, they're folded and rolled into large cylinders. Or here, they're wrapped and packed into rectangular packaging, and in which can be loaded onto transport and transported to site. And on site, they are loaded then onto the installation barges where they're wound around cylindrical steel drums and put over the side of the installation barge. For on-site fabrication, you actually require a similar flat area to what you would have in a factory. So in many cases, if you've got the area in the factory, it's better to do it in the factory because it's easier to control. Whereas on site, you don't tend to have this large flat area for the fabrication. It can get difficult to do. And so this can be a major consideration during the installation process. So then we take the delivery of the panels to the installation barges, where it requires the unpacking and rolling around the installation barge. Now, there are two common modes of installation for these marine structures. First of all, we have the fabricated panels on large rolls. They're loaded on the installation barge and then unrolled at a specific location. And we can see here in the diagram in the top left, where here we have the installation barge where the panels have been rolled around a large cylinder, and then it's lowered onto the seabed, and then the installation barge moves away and the reinforcement is laid out on the seabed. And you can see here in the photograph on the right, one of these installation barges where the reinforcement is rolled around the cylinder drum. And just to give you an idea of the scale here, these are some 25 meters in length, the reinforcement. And it's pushed off the side of the installation barge. And you can see down the bottom right, goes off the side of the installation barge into the water where it sinks to the seabed. Now, the other way of installing these panels is you may want to fabricate them on a wide flat barge prior to installation. So here we have a wide flat barge, and these barges may be 40 or 50 meters in length. And the rolls are rolled out on the surface of the flat barge, and they're joined together by seaming. And as they're joined together, the barge moves away and the panels move off the side of the barge onto the seabed. And so you can install the panels in this particular means as you're fabricating them on a flat barge. Now let's come now briefly to marine seawalls, which is one of these reinforced fill applications. And this is where we're constructing them on soft foundations. Now, historically, soft foundations in these seawalls were commonly dredged. And the dredging was carried out to provide a stable foundation and to prevent instability and settlements. However, this was an expensive exercise, and along with accompanying environmental contamination problems, because as you're dredging the soft foundation, it may be contaminated and you may be disturbing it and mixing it up. And so it's not, from an environmental point of view, a very good solution. So this is what you have. You have the sand fill placed here, then the granular fill for the seawall, and then on top of that, the reclamation. Now, over the last 15 or 20 years, there's actually been a move towards more economical alternative type seawall structures. And an example of that is the use of basal geotextile reinforcement when constructing seawalls on soft sediments, as you can see in the diagram on the right here. So we have a soft foundation. Here we're placing the basal geotextile reinforcement, and then we're using granular fill on top to construct the seawall. The basal reinforcement is there to provide additional stability, but what must be remembered is the containment diet can still undergo settlement. So you have to take any settlements into account with the design of these seawalls. Now, the types of basal reinforced marine seawalls, you can have basically two different types. One type is where the basal reinforcement is used alone beneath the seawall on the top of the soft sediments. And here the basal reinforcement provides stability for the seawall. Depending on how soft the sediments are, the sediments in the marine wall may be significant, and you need to take that into account in the design. Also, you're having a lot of the time put armour protection on the seaward side of the seawall, and that can add significant weight, and that also needs to be taken into account. And the thing about seawalls is that you can have a significant vertical loading on the foundation of the seawall, and that over a relatively small area. And so that also needs to be accounted for. Now, what's occurred over the last 5 years or so is different types of foundation treatments have been used beneath reinforced seawalls. And one of the more common techniques is that columns have been inserted into the soft foundation layer beneath the foundation of the reinforced seawall. And the height and the angle of the seawall is designed to meet hydraulic stability requirements. But the foundation stability and settlements are countered by the installation of these foundation columns. And the column extent always needs to be extended beyond the toe of the seawall to provide stability for the seawall toe. Whereas in terrestrial pile embankments, it's the crest of the embankment that's important for stability. Whereas for a seawall, it's the toe of the seawall that's required for stability. Commonly, coarse granular fill is used for erosion resistance here. And again, a final armour protection is placed on the outside, and it may add extra weight. Modes of failure of basal reinforced seawalls and soft foundations. There are essentially 3 modes of failure. First one is toe stability and erosion protection, as shown here. And we spoke already about how the toe stability is important for a marine seawall. The second type mode of failure is a rotational stability, and this governs the basal reinforcement tensile strength to provide the required stability to the base of the seawall. And the key thing here is that the stability of the seawall and its toe can be the most critical factor in this design. The third type of mode of failure is the potential settlement of the seawall and the strain in the basal reinforcement. Normally what's done is the basal reinforcement strain is limited to a safe value so that the foundation doesn't overstrain. Let's come now to capping layers, reinforced capping layers on soft sediments. Normally what you have, the problem is you have the soft sediments, and this may be contaminated. And on top of the soft sediments, we place the basal reinforcement layer. And then over the top of the basal reinforcement layer, we place a capping fill layer to cover the soft sediments and to leave them in a stable state. Here, the reinforcement is placed on the seabed and it can be placed with a geotextile installation barge. And what we're trying to do is to limit the tensile stresses in this basal reinforcement as you install it. And this depends, the magnitude of these tensile stresses depends on the method of geotextile reinforcement placement. Capping cover is then placed over the top of the reinforcement. And the strength of the reinforcement here is to maintain the stability of the capping fill layer So you can control the amount of fill and how carefully it's placed so that you don't overstress the basal reinforcement layer, and so you leave a stable capping layer over top of these soft sediments. And the capping cover must be placed in such a way to ensure instability of the capping does not occur. Now, you can either place this capping hydraulically, in other words, you pump the fill on top. It can be installed dry through the water column, or it may just be dry dumped. And obviously, dry dump, you have less control over the amount of stresses that are applied to the surface of this. So you need to take some care with that. So with that said about the typical marine applications, I want to turn now to the case studies. And I have 3 case studies here. The first case study comes from Australia, and it's the Brisbane port expansion in Australia. Second case study comes from Vietnam, and the third case study comes from Hong Kong. So let's first look at the Brisbane port expansion in Australia. And what it entailed was the seaward expansion of the Brisbane port to increase port capacity. So an additional 230 hectares was used in the mouth of the Brisbane River in Moreton Bay. And so here in the photograph, at the top part of the photograph, is the existing Brisbane port. And this is what's being expanded. And it's being expanded here out into the Moreton Bay. And you can see them constructing it here with a seawall. And then inside it's reclaimed to construct the extra area for the port. And what they're placing is an additional 8 kilometres in length of seawall capacity for the port expansion. The reclamation in this area was formed from channel maintenance dredging in the Brisbane River, which is shown here. And here the average water depth is only around 3.5 metres in water depth, so it's quite shallow. And there are very soft marine clay sediments in the river estuary up from a depth of 8 to 30 metres. And here you can see a profile of the undrained shear strength at depth. And here's the undrained shear strength across the top and the depth down below. And you can see in the top 3.5 to 4 metres of the soft sediment. It's very soft. It's only undrained shear strength of around 5 kilopascals. And after that, it increases linearly with depth down to about 25 metres, where it becomes almost up to about 40 kPa in undrained shear strength. So at the surface here, it's very soft. And also this area here is close to the Moreton Bay Marine Park. And this is a very sensitive area, environmentally wise, and it wouldn't allow any sort of contamination or mixing of sediment in this marine park area, and it can't tolerate any sediment contamination. Now, these are typical sections through the marine seawall. And here you can see it was about 7.5 metres high to total height above water level, of which around 4.5 metres was a dredged sand fill here. You can see the basal reinforcement placed across the base, some 40 metres in length. And the strength of this basal reinforcement varied between 400 and 800 kilonewtons per metre, depending on the geometry of the problem. Then sand fill was placed hydraulically over the top of the basal reinforcement, and it raised up to the water surface level. Above this, a geotextile filter was placed across the top of the sand fill. And then on top of that, the rock fill and rock armour was placed in the dry on top to construct the seawall. So here in the bottom left hand, you can see then placing the basal reinforcement. You see here they've used a flat barge. This is some 40 meters in length. And on this flat barge, they roll out the roll of geotextile reinforcement. They then sew it together on top of the flat bottom barge, and then they move the barge in this direction to the left, and the geotextile reinforcement goes over the side of the barge onto the seabed. Here you can see another shot of this flat barge here. This is the basal reinforcement. You can see placed some 40 meters in one single piece. And here they've pumped hydraulically the sand fill on top of the basal reinforcement to the waterline. And then over the top of this sand fill, they've placed a geotextile filter over the top. And this geotextile filter is placed off the top of an installation barge. So it's rolled onto a circular drum, and you can see the circular drum here. The geotextile filter placed over the side of the installation barge onto the top of the sand fill. Then the barge moves off to the left, and the geotextile filter is left in place. And then over the top of this, the granular fill and the rock armor is placed out of the waterline on top of the geotextile filter. And you can see down here in the bottom left hand, this is the rock fill and the rock armor protection. It's closing off the seawall here. And you can see the seawall has been closed off here. And this is the armor protection placed on the outside of the seawall. Now I have the second case study. And this is the deep C2 reclamation from Vietnam. And this is a large, at the time, was a large industrial site development carried out in different stages in the Red River Delta area of North Vietnam. At the time of this development, it was the largest private industrial development in all of Vietnam. The project was actually a staged construction and expanded as demand requires over time. And here you can see a photograph of part of it. And this is actually the C2 reclamation part, where you see here's a series of basal reinforced seawalls extending out as demand increases here. And then the area in behind is filled with sand fill to create the industrial land. In the bottom left diagram here is a site layout. And for those of you who are familiar with North Vietnam at all, this is Haiphong City. And Haiphong City is the major port for North Vietnam. So it's on the coast in the delta of the Red River in North Vietnam. And these are the developments for the reclamation scheme, this industrial scheme. And they're made in different zones in areas as they developed, all the way out here. The slides I have is actually this one here. This is deep C2. This is this grey area too. But the same technique was used in all the different developments for bringing all the way out in the Red River Delta. The thing about this area is that water currents are very low, and you can see in the top photographs there, really low water currents. Tidal range is low, only maximum about 1.5 meters. And normally low water level coincides with the surface of the soft sediments for a large part of this area here. However, while tidal range is low, water currents are low, the area is subject to extreme storm events from typhoons. And for those of you in Australia, typhoons are cyclones. So that'll probably be more familiar for you in Australia. And they can, of course, be very, very destructive. The soft soils in the foundations here are very soft organic clay foundations with depths up to about 15 meters, and you can see at the surface. It's about 5 kPa undrained shear strength, increasing linearly with depth, up to about 30 kPa, about 15 meters depth. And then below that, the stiff gravels and clays and to depths of over 35 meters. So it was really these surface foundation conditions which had to be taken care of in the construction of these containment dikes for this reclamation zone. Now, the way these containment dikes were designed, they were designed to about 4.5 meters in height, here to the crest of the containment dikes. The containment dikes were made from sand fill, and they were constructed on top of basal geotextile reinforcement, some 35 meters in width. And the strength of the basal reinforcement was 800 kilonewtons per meter. Now, the basal reinforcement was actually installed during low tide. Of course, at low tide, the water level was almost at the same level as the surrounding soft foundation soil. So they could do this from a surface technique, installing the basal reinforcement. Then what they did for the containment dikes, they used geotextile tubes on the periphery of the containment dike. Now, for those of you who don't know, geotextile tubes are long geotextile sausage-like materials which are pumped hydraulically with sand fill to create a tubular structure. And the geotextile skin prevents the sand fill from eroding out through the geotextile tube and provides a stable geometry. And you can see here one of the containment dikes being built. You can see here they use bamboo fascines with the basal reinforcement as the foundation reinforcement. And then at the edges, the geotextile tube on this side, and then also on this side, and then the area in between will then be filled with sand fill, as shown here, to construct the containment dike. And the geotextile tubes on both sides of the containment dike were there to provide a permanent erosion protection for the dike until the next expansion stage occurred. And so even during typhoons, these geotextile tubes were to provide the erosion protection. And once the development had fully occurred on the landward side, and it came time to further expand the geotextile the dikes, and these were expanded, and then the reclaimed fill was placed over the top of this to construct the additional area for the reclamation. Now, one thing about these geotextile tube protection, and you can see here, they're permanently exposed. And they're required to have an exposed design life of around 5 years before it was assumed that the next stage of the reclamation expansion would come along and cover all this over to create the next area. Now you can see in this top right-hand photograph that this is about 5 years later after it was installed. And you can see the condition of this geotextile tube is very good, still very stable, tube's working, it's retaining the containment dike, so it's all working very well. But we'll have to say it all didn't happen quite like that. At 1 or 2 stages, the contractor who was doing the work decided he would try for a very cheap geotextile tube to use. And so he was supplied geotextile tubes with no UV stabilizer in the geotextile tube. And you can see this photograph here is taken less than a year after the tube installation. And you can see the tubes have been degraded by the sunlight. The sand fill in the tubes have just been eroded out down the slope, and the whole area has collapsed, and so it's not very good at all. So in this particular case, the contractor had to go back and replace these degraded tubes with proper geotextile tubes that would last for the required 5 years, as shown here. So when you're using these geotextile tubes for long-term exposed erosion protection, it's very important to ensure that the UV stability of these tubes is adequate to last for the required period of time. Now I'll come to my third case study, and that's the Hong Kong International Airport, the third runway expansion. Now, a lot of you may have heard about this project. It's quite a big, sophisticated project in Hong Kong. And if you go on the internet, you'll find several YouTube videos that are available on this large project to explain it to you. Here, in this photograph, you can see in the foreground, this is the third runway expansion here in the foreground. And these are the taxiways associated with that. Back in here, this is the infrastructure and logistics development area being constructed for this expanded reclamation area. And then in the background are the original runway 1 and runway 2 runways of the original Hong Kong International Airport. So primarily what we're going to be talking about is this part of the reclamation here, down around here, and the seawall, associated seawall with this project. Now, the project overview for this expansion was to provide an additional capacity for an additional 30 million passengers per year. And so a new additional reclaimed area expansion to the north of the existing airport. So here is the existing airport to the right on reclaimed land. This is the existing terminal facilities here in the background. And then off to the left, which is actually to the north, this is the new reclaimed area. And this is the third runway expansion, the new third runway expansion. And this is a new additional terminal facilities. Cost for this additional facilities was around $20 billion in cost. And it's located deeper out into the water than the existing reclaimed area in 5 to 8 metre water depths. The reclamation is located on very soft alluvium and old contaminated mud pits, and I'll show you some more details of this shortly. And because of the environmental considerations in the area, they weren't allowed any disturbance from any dredging operations were allowed. So therefore, a variety of non-disturbance foundation treatments throughout the reclamation was carried out. So dredging wasn't allowed. And in this expansion, as we'll see, large quantities of geosynthetic filter layers were used, geosynthetic reinforcement layers were used, geotextile tubes were all used as integral parts of the reclamation construction. Now, I haven't got slides on this, but additionally, PVDs or wick drains, if you want to call them that, and surcharging was also used in other reclamation locations. And the main part of this reclamation supports a 3.8 kilometre long runway and extra concourse buildings here. So in this third runway location here, which is to the north of the existing reclamation, about 40% of the reclamation is recovered over contaminated mud pits. So you can see the grey areas, these are contaminated mud pits. And these mud pits were developed from reclamations in the city of Hong Kong where the dredged self-sediment was carried to the mud pits and dumped in the mud pits. And a lot of these were contaminated with industrial effluent, things like this. And so it now came the time to reclaim over the top of these contaminated mud pits. And these weren't allowed to be disturbed because we didn't want to environmentally damage other local areas. Very low shear strengths and high compressibilities in depths of 20 to 25 metres. And here you can see a plot of the foundation undrained shear strengths. This is around the edge of the seawall. So going around the edge of the seawall here. This is going around the edge of the seawall. You can see the blue shaded area is marine deposits, very soft. And you can see down here, and these go down to about 20 metres in depth. Now, for the foundation for the columns, which were put beneath the runway area, and we'll see these columns in a moment, they had to be extended into this foundation material some 5 metres or so. And so they had to be ended in this crosshatched area down here. And you can say this depth is around about 25 metres depth below sediment, top sediment surface level. So these had to be the depths of where these columns had to go. So these had to be quite deep in the foundations here. So these foundation treatments, they had to provide the required bearing strength and stability without disturbing the contaminated mud layers. And so the technique that was used for these columns, this technique was called deep cement mixed columns, DCM columns. And this is a technique quite commonly used in Japan and Korea, but not used in Southeast Asia up until this time. These were installed into the soft sediments to depths of 20 to 25 metres in pre-planned layouts. Now, these DCM columns utilise cement grout injected soft clay. So these drills were drilled into the soft clay, and then as they are withdrawn, cement grout is pumped into them to create the column, and then they're drawn out of above the soft sediment layer, leaving the column behind. And the geometry of these columns, in this case, were constructed as square type units. Each cylindrical thing was 1.3 metres in diameter, and that gave a square column of 2.3 metres in diameter. Now, this is one of the barges used to install these columns. You can see here the equipment used was quite large, and there was a large number of these used. And these were the deep cement mixed columns were installed down into the foundation and then withdrawn. Well, the spacing of these columns was just under 5 metres, and they were built in the form of a retaining wall beneath the seawall, and they were built in the form of individual columns underneath the third runway, as we'll see shortly. Now, across the tops of the DCM columns, a geosynthetic reinforced load transfer platform was placed and installed before the reclamation fill was placed, and we'll see that in a moment. Now, other types of geosynthetics that were used in the area, first of all, non-woven geotextile were used as separator and filter layers over the soft marine clay from the sand reclamation fill at different locations throughout the reclamation spot. And you can see here it's replaced from an installation barge. These are some 30 metres in width here, and placed at different locations on the seabed before the sand fill's placed. And you can see even up the sides of the seawall, the geotextile filters placed here and then on the seabed. And around 7 million square metres of non-woven geotextile filters was used at different locations throughout this site. Then when it comes to the geotextile reinforcement, here we have a section through the reclamation. And here you can see on the left is the seawall, the outer seawall. And you can see beneath the seawall, these DCM columns have been installed in the form of a retaining wall, or big tall walls, where about 4.8 meters apart, but in a continuous retaining wall across the base of the seawall. And so what happens here is a single layer of geogrid reinforcement was placed across the base of the seawall, across the top of these column walls here. And these geogrid material, as you can see here, is very strong, some 800 kilonewtons per meter in strength. The panels were 150 meters long by 25 meters in width, and about 600,000 square meters of this high-strength geogrid was used beneath the seawall. Then when we come further in, we have this transition layer where stone columns and surcharge have been used. And then here we come to the location beneath the third runway. And here the DCM columns are used as individual columns. And across the top of that, the woven polyester geotextile reinforcement of 1,000 kilonewtons per meter was used across the base of the third runway in two orthogonal layers, one layer in this direction and one layer along the length of the runway. The panels here were 200 meters long by 25 meters in length. And again, some 2.5 million square meters of basal reinforcement was used in this location beneath the runway. Now let's come back to the seawall again. So here we have the seawall core, the geogrid reinforcement in a single layer, and then the DCM walls underneath that. And as I said already, 800 kilonewton per meter geogrid used in a single layer as part of the load transfer platform at the base of the seawall. The reason why only a single layer is used because it had a 2D loading, because these are actually wall units and not individual column units. The geogrid panels were loaded onto the installation barge and assembled, fabricated on the fabrication barge. And you can see the large cylinder here with the geogrid reinforcement rolled onto it. And then it goes off the surface of the barge and then into the water. And here you can see where the seawall comes out of the water alignment. You can see it's quite granular fill in the seawall here. And then underneath the seawall is the geogrid basal reinforcement.
Chris, we have 10:55. So if we can slowly wrap up, that would be great.
Okay, give me, I'll go through this slide. I'll go to the next slide. It's more important. Okay. So let's come out of the third runway expansion where the woven geotextile reinforcement was used beneath the third runway, where we had the two layers of 1,000 kilonewton reinforcement as a load transfer platform. And you can see here that the columns, the two layers of reinforcement, and then the reclamation fill placed on top. And so the reinforcement was fabricated up into the factory. And you see it takes quite a lot of people to fabricate it, and this high-strength seams sewing it together. They roll into cylinders, and then at night they'll transfer to the site when traffic was quite low. And then at the site, they were loaded onto the installation barge. The installation barge was taken to site and loaded on and then installed on the seabed, moved across the surface of the seabed. And you can see here where the geotextile reinforcement is sinking onto the seabed. Now this is the reclamation where it's come out of the waterline. You can see the seawall here. This is the area of the third runway, and the taxiway is here. This is a little bit later. Again, the seawall, the third runway, and this is the surcharge on the taxiway area here. Now, this is a picture of later on where the runway is almost complete, and these are the taxiways. And this area was actually opened in late 2025. So it's about 4 or 5 months old at this stage. And just some concluding remarks on this particular Hong Kong case study. I think you'll all appreciate that this was a large-scale, sophisticated marine project. And it would have been really impossible to meet the performance requirements without the extensive use of geosynthetics. And they were used for a range of applications, reinforced fill structures beneath the seawall, also used for separation filter layers, and also used for some of the on-site works as well for the geotechnical tubes. My overall concluding remarks for the presentation is that the move from terrestrial on land to marine and water applications, while outrightly quite straightforward, has presented some interesting challenges and complexities for marine fill structures. While the overall design principles remain the same, the techniques used for the installation of the geosynthetic reinforcement are more complex when influenced by the presence of water and erosion forces. We have the two main types of marine reinforced fill applications: basal reinforced marine seawalls and basal reinforced capping layers. And I've given you a bit of a rundown on both of those. And the key thing about the role of the reinforcement, it prevents instability of the marine structure and the dissipation of any contaminated sediments below. Thank you. Almost to time.
Thank you so much. We'll go now to Glenn Gillan with Solmac's presentation. And in the meantime, if you can type your questions in Q&A sections to Chris or to Glenn as well.
Thanks, Alicia. I'll keep this brief given the time, but thank you, Chris. That was very good. And a lot of my presentation ties into what Chris spoke about. I'm glad he went into a lot of detail and saves me having to go to as much detail, but I'll just hit the main points and how Solmax can be of assistance to deliver projects, just as Chris highlighted. Solmax has the widest reach. We're a global manufacturer, the largest manufacturer of geosynthetics around the world. And the dots on each of these locations show where there are manufacturing plants, which has proven quite useful in the current global situation with the Middle East conflict ongoing, which has made it very difficult in the land of geosynthetics or anything manufactured from plastic polymers or oil derivatives. And it's allowed Solmax to continue to find raw materials and keep producing, even though where we were traditionally getting it from for this part of the world has now become offline. In addition to the strong manufacturing plants, Solmax invests in technical expertise in salespeople, and we serve more than 110 countries around the world, more than 250 sales and marketing or technical engineering experts throughout the organization, which creates a fully dedicated team of engineers, technical personnel that can assist on your project like that. And some of the examples Chris showed there, it's more than just the supply of material. You know, certainly need high quality materials, and there were some examples of some inferior materials used on some projects. But it's also the technical expertise and working with a supplier to deliver an outcome. And when panels need to be manufactured together and an installation technique is going to be quite complex, it's not just a straightforward installation of rolling a roll out and putting material on top. Often they're quite complex. So Solmax can certainly assist with all of those sorts of things. Across the portfolio, we can cover any customer need that may be faced, whether that's separation, requirement, reinforcement, filtration, drainage, barriers, and Solmax has a portfolio and range of products to do that, each of those being listed there. But the one that we'll talk about predominantly, which ties into most of what Chris spoke about, was the high-strength reinforcing geotextiles. Here's a photo of what they can look on the right-hand side there. They're made from high-tenacity polyester yarns with proven long-term design strength. They're ideal for the reinforcement applications over soft soils, piles, cavities, marine applications, and terrestrial applications. They're very cost effective and efficient, and they can be stitched together into multiple panels in different lengths, widths, and configurations to suit the customer need. Here's some photos that, again, look similar to the ones that Chris presented, coming from the same factory. The panels can be manufactured in a range of widths, lengths, and then folded and wrapped up. So they're not traditional, or they can be in traditional rolls, as you would expect in standard sizes, but they can also be customized into specific panel sizes, which is similar to how Chris presented in marine applications. We've done a lot of projects in tailing situations where the tailings may be too soft to even walk across. And so you need to find a solution to get materials across, and you can't just drive an excavator across or pull it out by hand because the subgrade's too soft. So being able to manufacture custom sized panels has been very beneficial for that. And in a range of strengths from 200 kilonewtons all the way up to 2,500 kilonewtons. And we're pushing that envelope further to try and get that even higher. I'll just quickly work through. Chris covered a number of case studies here, so these are less important, but similar to his marine application, here was a tailings closure in New South Wales that had very soft subgrade, so they used a range of different strength Merafi PET products that are very high strength woven geotextiles, and these require different panels in different lengths from 130 metres all the way up to 200 metres. In Shute Harbour in Queensland, this required customised panels as well. They needed a lot higher strength in this project, up to 2,000 kilonewtons per metre. That was used under the reinforcement of the rock armour revetment. This was subject to terrible erosion and breakdown after a cyclone went through, and the reconstruction required a much more significant upgrade, and the use of geotextiles came in very handy for that project. And the final one here, I've just got a Cape Preston iron ore project. In this one, PT 800 was used across different layers to build up the subgrade. It had lack of strength. They needed to put a 7-metre high rock embankment over the top of it. And here, Merafi PET was the chosen solution in multiple different layers to get that strength over a very soft subgrade. As you can see, the extent of the saturation around the bund that they built there. So in closing, you can see just sort of in the photo here, I tried to find a photo where it showed a highlight or an example of the customized solutions that Solmax are able to put together. When you need performance, that's Solmax strength. We're the largest manufacturer in the world. We can provide custom solutions, be that changes in lengths, custom widths, stitching multiple panels together. We can get very, very high strengths with very innovative options to use there. And we have an army of technical personnel ready to assist with your project. So if you do have a project there, here's my details. Feel free to get in touch. We'd love to be of assistance, and thank you for your attendance, and particularly thank you to Chris for his very insightful presentation.
Thank you, Glenn.
Yeah. Thanks, Chris. Thanks, Glenn. Just there's a whole bunch of questions, so if we can, I'll try and whip through them because some of them are quite interesting. First of all, the number of comments early on about the noise and the echo. Hopefully that improved. It was working okay for me, but hopefully that improved as the talk went on. The video will be available later. The presentation won't be, but we'll have that on YouTube within a week. So stay tuned for that. A couple of questions, Chris, on the case studies. The first one around the case study in Vietnam. You had bamboo mattresses on the geotextile layer or underneath the geotube. What was the reason behind this, and are there any alternative solutions for that approach?
The use of bamboo with basal reinforcement has become a fairly, what I'd call, I guess, a common technique in countries like Indonesia and Vietnam. And the on-site labour is very cheap, and they tend to do a lot of manual work rather than machinery-based work. Now, obviously, if the subgrade and the foundation conditions are very soft, then to help people walking on top of it, walking on top of the basal reinforcement, is to place a layer with some bending stiffness on top of the reinforcement. And this is what the bamboo raft does. It gives some bending rigidity to the base, and so enables, from a constructability point of view, it makes it easier to build. And so it's really a type of technique which is used in Vietnam and Indonesia. It's not generally used anywhere else, but it just tends to have grown in that local environment.
Another question on the Vietnam case study. Why did it use sandfield mattress? I think maybe it was geotube on the seaside dike slope. Why not use concrete mattress or rock armour?
Basically because that containment dike was not the final alignment of the containment dike. It was an initial, one of the stages of construction. And so even on the seaward side, the geotextile tubes were used because later on, after maybe 4 or 5 years, they would come along and they would extend that reclamation even further into the seaward side with another containment dike. And it would only be when they got to the final alignment of the containment dike, where there was no more expansion to be carried out, would they build the final rock armouring on the containment dike. That was just an interim solution.
General question, Chris. Any concern for polyester's hydrolysis resistance?
You mean in water, I take it. Polyester, the type of polyester used for soil reinforcement is highly stable where it comes to hydrolysis, and so the type of high molecular weight, low carboxyl N group polyester polymers that are used for reinforcement, the hydrolysis resistance in normal conditions is probably less than 5% over 100, 120 years in normal environments. So the effect is basically nil. And so for hydrolysis of polyester for soil reinforcement, there's really nothing to worry about. Now, let me just add something to this, because what people sometimes read is they read publications that were written 30, 40 years ago. And the types of polyester polymers that were available 30 or 40 years ago were quite different to the polyesters used today. A lot lower molecular weight, a lot higher hydraulic N group counts, and so the rates of degradation are quite different. And so you shouldn't be comparing publications and what you read from 30, 40, 50 years ago with what's available today.
A question around installation. The bigger the geotextile panel, does that mean heavier equipment needed? Does it mean installation costs may be higher for bigger panels? Considering, I think in your case studies, you had some of them are over 200 metres in length and 25 metres wide.
I think it is for efficiency and cost efficiency of installation. If you can install to the biggest panel size, then it's more efficient. Now, I'd counteract that with, it depends on the size of the project. In the case studies I showed there, the project, especially the one from Hong Kong, the projects were very large, so it was worthwhile for the contractor to have several of these large installation barges, which made installation of the reinforcement pretty efficient. Obviously, if the area is a lot smaller than that, then it might well pay the contractor not to have quite as bigger installation equipment and to concentrate on smaller installation equipment, which is easier to do. It just depends on the scale of what the contractor does.
Port of Brisbane, spark this question. Is there any problem if we put rock armor directly on the geotextile filter, such as breaking or punching through the geotextile filter layer?
No, there wasn't. And there was quite a lot of studies done on this. We're testing out different types of geotextile filters to see whether they would be suitable for that type of rock armor to be placed directly on top with no puncturing. So the contractor went through an evaluation program before he arrived at a suitable geotextile filter. Now, the type of geotextile filter he ended up using was a very thick, robust, I think it was about 1,200 grams per square meter needle punch geotextile filter, which could resist the stresses caused by that rock armor being placed on top.
Yeah, I think my recollection was there were rock drop trials and all sorts of activity, Chris, to get that
That's
right.
right.
A detailed question here about Hong Kong. Load transfer platform often used for transmitting vertical load. However, in the case of the Hong Kong airport, DCM is used for a seawall, and that can push DCM laterally. In design, did it consider the geogrid used to restrain lateral displacement to limit DCM broken or damaged under lateral load? Noting that DCM column very weak under lateral load.
Yes, the consultant who designed it did take that into account. And another under the seawall, you remember that individual piles, the DCM columns weren't used under the seawalls, in that they are used as continuous wall units across the width at the base of the seawall. And so there it was assumed that for the wall units, that these wall units would resist any outward thrust or any outward deformation that may occur from the geometry of the seawall. So that would be taken up not in the reinforcement, but in the DCM columns.
And the last question we have from New Zealand, the interaction values of the woven reinforcement change from what is used for terrestrial applications versus underwater applications for stability analysis?
The answer is no, and that the loading onto the reinforcement was assumed to be approximately, well, I better clarify that. I'll say approximately the same. Now let me come back and clarify that. The interaction factors in terms of friction and things like this were accounted for in terms of the hydraulic conditions where it was used on site in Hong Kong. So it was assumed that the friction angle, effective friction angle, wouldn't be the same as what it would be if it was in the dry, and that the effective friction angle was used as part of the design, as if it was underwater. So they were taken into account, but the values weren't very much different.
And so I said it was last, but just quickly, Chris, what software can be used for analysis of the tensile strength of seawall basal reinforcement?
I think that, well, historically, a lot of the analysis used were limit equilibrium analysis, with slip circle type analysis, which gave a pretty good history, and for standard geometries, they gave pretty good results. Where they fell down a bit was some different conditions in marine cases, which you have to take into account. Some of these equilibrium analysis methods don't take that into account, and for non-standard geometries, they're not so good at that. What's come along though in the last sort of 10, 15 years or so is these continuum methods. And by continuum methods, I mean finite element and finite difference type techniques. like Plexus and like FLAC and things like that. And they're much more sophisticated, and they can take into account a whole lot of different conditions for these type of techniques. And they can give quite good answers. The thing about them are, you know, quite sophisticated, quite a high learning curve, and you need to put the right parameters in to get the right results out. Otherwise, you know, you get garbage in, garbage out. So you have to be careful with them, but they have become very user-friendly. They give nice graphics results, and you can see easily what's happening and things like this. So they tend to be more commonly used these days than, say, limit equilibrium methods. Although limit equilibrium methods are being used, but mainly still just for standard type applications.
Okay, thanks, Chris. And Port of Brisbane was 2005, so I don't think there was finite.
A long time ago. And
Thank you very much.
And it's still standing.
Yeah, it's still standing. Thank you very much, Chris. Thank you, Glenn. And hand back to you, Alicia.
Yeah, thank you, everyone. And we invite you for another webinar series. Chris, it was a pleasure to have you here. Bye.
Thank you. My pleasure.